Hi guys, Professor Ajiri here. Just a couple things. I wanted to let you know that I did take down the week 4 virtual lab. I did try it again and I was having issues with it and it wasn't allowing me to do the precise feature like it was when I first started. And believe me, I will never sacrifice course material, but what I do want you to do is have enough time to focus on this week's new material as well as the exam, which contains this new week's material. So I'm gonna actually do what you will do for the lab. Excuse me, no, you won't submit the lab. But this is good practice for some of the questions on the exam. So I'm gonna walk you through the work that I did for pre-lab questions 1 through 4 on the Stoichiometry virtual lab, which includes figuring out net ionic equations. So I'm gonna film this and post this, and then I'll do a couple others. And honestly, and I know I posted this on the Blackboard site, I think that it might be more beneficial for me to do some video recordings of walkthroughs of problems rather than just narrate the PowerPoint slides sometimes. So if anyone disagrees with this and would rather have me record the rest of chapter 7, I will gladly do that. But if you think it's more useful for you to see some of the problems done out by me, then I'll continue to do so. So I am actually going to also post static pictures of these so that you can have them at your disposal for reference. But I'm going to walk you through what I did here for the Stoichiometry virtual lab. So the first question says, write out a reaction for solid sodium chloride added to aqueous silver nitrate. So sodium chloride, just the tiny S denotes that we're adding solid powder. Everything else, well here, right, the reactants, what you're putting in is the silver nitrate, and it's dissolved in water, so it receives the aqueous designation. Okay, now we only have one of each of these atoms, right? This is a polyatomic guy right here, the NO3. So out of this, and you can feel free to Google this stuff if you're unsure, right? The sodium is going to end up pairing with the nitrate ion. So this is a +1 and a -1. And this is a +1. Excuse me. And the chlorine is a -1. So they're going to pair. Okay. Now, we know that this is going to be some form of a precipitation equation. Okay. Meaning that we end up getting out of it solid, solid silver chloride. Okay. Now, for this, to know this, if you weren't familiar, and chances are people are not familiar with this, you're going to go to that table. I think it's table 7.1 in the text, and look at ionic solubility rules, right? This guy right here is going to precipitate out, which facilitates us being able to answer the next question. So this is, write out the net ionic equation for aqueous, right, dissolved in water, sodium chloride, and added to aqueous silver nitrate. So here, the only difference is we're starting out with aqueous sodium chloride rather than solid, as we did in the first one. Now, to write out the ionic equations, we're going to break these substances into their requisite or corresponding ions, right? So sodium chloride, I could have written this in the other direction, I just flipped it. Sodium chloride gets broken up into a +1 sodium ion dissolved in water, right? Because we're adding aqueous sodium chloride, as it says. And then a -1 chloride ion dissolved in water. Same thing for the aqueous silver nitrate. We have a +1 silver ion, aqueous, and a negatively charged nitrate ion, aqueous. Now, in the Chapter 7 PowerPoint, it does mention spectator ions. What ends up happening is the only thing that actually precipitates out and recombines to form something different is the silver chloride. Okay, so the nitrate ion and the sodium ion, these stay in solution. So even though they form a molecule, they technically stay dissolved. So we get rid of them. We cross them out. Okay, I wrote it here in red that they're spectator ions. And so our net ionic equation, once we get rid of the nitrate and the sodium, is aqueous silver +1 plus the negative chloride -1 precipitates to form insoluble sodium chloride. So for number 3, if we have 4.52 grams of the precipitate formed, how many grams of sodium chloride reacted. So the first question to ask is, what is the precipitate? The precipitate is whatever came out of this equation as a solid, which was silver chloride. Okay? So I've walked through some of this on Zoom calls with a few of you, and I had said I was going to post this. So this is one of the examples that we talked about. Okay, but this goes for everybody. This should be useful for everybody. Look at the original equation. Okay? There were no coefficients, no whole numbers to the left of each formula. So the assumption, right, if there's no coefficient, it must be 1. It's assumed to be 1. So we know that for every one molecule or for every one mole, right, we can do it either way. We can assume that this is 1 molecule of sodium chloride, 1 of silver nitrate, 1 of silver chloride rather, and 1 of sodium nitrate. Or we can assume that these are moles. 1 mole of this plus 1 mole of this yields 1 mole of that and 1 mole of that. Either way, we're going to assume that these coefficients are 1. So, for every molecule or mole of the silver chloride that we were producing, that means that 1 molecule or 1 mole of sodium chloride is reacted. So we come over here, right? We know that there's a 1-to-1 ratio between the molecules or moles of sodium chloride put in and the molecules or moles of silver chloride that are produced. What other piece of information do we know? We know that we made 4.52 grams of silver chloride precipitate. So, the question to ask is, how many moles is this? Why is that important? Because we want to know how many grams of sodium chloride had to initially be put in. But we can't just say, oh, we have 4.52 grams of silver chloride, so we must have 4.52 grams of sodium chloride. Why not? Because silver and sodium have different atomic masses, right? They're different atoms. So we have to convert the amount of silver chloride that precipitated to moles, because we know there's a 1-to-1 molar ratio of silver chloride and sodium chloride. So then we can convert back to grams when we know how many moles of sodium chloride we have. So to convert from grams to moles, we need to use molarity, the big M, as our conversion factor, right? And the units of molarity are grams per liter. So we know we started out with 4.52 grams of silver chloride, and I always put it over 1 just visually so I can cancel out numerator and denominator. Over, I'm going to flip the molar equation so that grams are on the bottom, so they cancel. I put right here, you can find the molar mass of anything, right, in this case, silver chloride, either by adding up the individual atomic masses or mass numbers for silver and for chlorine, or you can just Google it, right? I'm not expecting that you're living in a cave, so if you want to just Google it, make sure that the formula you Googled, since a lot of times you can't do super and subscripts, is the right one. So the molar mass, right, if this was molecular mass, this would be AMU per molecule. This is molar. So 1 mole of silver chloride weighs 143.32 grams. Grams cancel, so you're going to get the number of moles of silver chloride by dividing 4.52 by 143.32, which gives us 0.0315 moles of silver chloride. Okay? Now actually I have one too many significant figures here, right? It actually should be 0.32 when you do this out. Now remember, there is a 1-to-1 ratio of sodium chloride and silver chloride. So if we have 0.0315 or 0.032 moles of silver chloride, there are also 0.0315 or 0.032 moles of sodium chloride. So in our original question, we wanted to know how many grams of sodium chloride needed to be put in or reacted in order to form this much silver chloride. So here's your answer. Right now, this time it's going to be different. You're going to flip this. You're going to keep molarity in grams per mole because you want to get rid of the moles. So you're going to multiply 0.031 or 0.032, it should have been, times 58.44. And so it ends up, you put in 1.84 grams of sodium chloride. Okay, and then for question 4, it's if 152 milliliters of sodium chloride reacted in question 3, what is the molarity of the sodium chloride solution that was used? So remember, now when we're dealing with this, they're saying that you're putting in aqueous sodium chloride for this. So pretend you have a glass bottle full of sodium chloride solution, and however much of that you added, okay, which was 152 milliliters, we know that addition of that 152 milliliters of whatever that molarity solution was gave us 0. What was it? 0.312 or 315 moles of sodium chloride and 1.84 grams. So I came over here, right? We know that we want molarity of the sodium chloride solution that was used. So we know that out of that metaphorical stock bottle, the problem says that we took out 152 mils, and we know from question 3 that we had actually, and I have it on that page too, we have 184 grams of sodium chloride in the original solution with all the chemicals. So molarity is just grams per liter. So we have to get the 152 mils into liters, which we do here, right? There are 100 milliliters in 1 liter, so we have 0.152 liters of sodium chloride stock solution. And we know that that stock solution had to contain 1.84 grams of sodium chloride. So we divide 1.84 grams of sodium chloride by 0.152 liters to give us 12.105. We can only keep 2 sig figs, okay? So, or 3 rather, so it's 12.1 grams per liter is the molarity of the sodium chloride solution that was used.